Hi everybody, welcome to the first screencast that we're doing. This one's going to be about gases and gas laws. I know that you've done your simulation now, so you've seen a little bit about how gases behave, and so we're going to talk a little bit more about that now, and then we'll go from there. So the first thing that you should have seen in that simulation was just thinking about the idea of pressure and what is pressure. And so you should have noticed that as you were working through that simulation, that pressure is just a way to talk about the amount of force that's being exerted over a given area of space. And so there are lots of things that will impact the pressure. You saw some of them as you worked through the simulation. But in general, all of them sort of come back to this idea that the more collisions there are with the sides of the container, for whatever the reason is, there's going to be greater pressure. And that's sort of going to be our guiding principle when we're thinking about pressure. So there's a bunch of different ways that we can look at units of pressure. The three most common ones that you'll see in chemistry are kilopascals, millimeters of mercury, and atmospheres. So kilopascals get abbreviated kPa, millimeters of mercury gets abbreviated mmHg, and atmospheres is just atm. These values here are the standard unit for that pressure, or that unit of pressure, I should say. And you'll see that this is what we consider to be the pressure, atmospheric pressure at sea level, is what we're going to consider to be standard pressure. And so at some point earlier in the year, we talked about this idea of what's called STP, or standard temperature and pressure. And basically standard temperature and pressure is just a set of conditions that we often refer to. And so standard temperature is 273 Kelvin or 0 degrees Celsius, which remember is the same temperature. And then standard pressure is just pressure at sea level. So any one of these three values, depending on what unit it is that you're using, it could be 101.3 kilopascals, it could be 760 millimeters of mercury, or it could be 1 atmosphere. So the other thing that you saw in the simulation was about kinetic energy. And so we've also talked a little bit about kinetic energy this year, and just the idea that kinetic energy is that energy of motion. And when we're talking about gases especially, the kinetic energy and the temperature we're going to think of sort of interchangeably. So as the kinetic energy increases, the temperature is going to increase. So as the particles are moving faster, we're going to think about that being a higher temperature or a hotter gas, and vice versa. The other thing that you saw in the simulation is that when there's no kinetic energy or no motion, we typically associate that with 0 Kelvin, which we call the absolute zero. And we talked about that also back in the first semester. So the most common variables that you'll see used in these gas laws that we're going to talk about are pressure, volume, temperature, N, which is going to be used to represent moles, and then this constant R, which is called the gas constant. And the gas constant kind of has this complicated looking unit. It's kilopascals times liters per Kelvin times moles, and that unit varies depending on what unit you're measuring pressure in. So it just kind of depends on the circumstances. And later on, you'll watch a Khan Academy video that's all about using the ideal gas law, and there'll be a little bit more explanation about that constant R. So there are quite a few gas laws. The first three we're just going to go through kind of conceptually. We're not going to get into the math right now. And then the ideal gas law, you'll do some math with the ideal gas law, but not right now. So the first gas law that we're going to look at is called Boyle's law, and it's basically a pressure and volume relationship. And the idea with this is that if you imagine a container full of gas with an initial volume of 8 liters, if you imagine being able to shrink that volume down to 4 liters, so half its original volume, if you have the same amount of gas trapped in the container, what's going to end up happening is that the pressure is going to double because there's half the amount of area now in here and the same number of particles. And remember that pressure is just force over area. So if you have force over area and there's less area and there's the same number of particles, that means that the pressure is going to be greater. And so this pressure-volume relationship is a indirect relationship. So as the volume decreases, the pressure is going to increase, or vice versa. And you'll see it mathematically here. So when the pressure increases, the volume decreases. When the pressure decreases, the volume increases. This is an inverse relationship. And this is what the gas law would look like. But again, we're not going to worry too much about the math of it right now. The second gas law, the second relationship that we're going to see is called Charles' law. And Charles' law is a volume and temperature relationship. And so a volume and temperature relationship is basically saying that if you have a fixed amount of gas and you decrease the temperature of that gas, so if you went from your warm house outside on a freezing cold winter day and you had a balloon in your hand, and maybe this has happened to you before, you would notice that that balloon all of a sudden is going to shrink because when the temperature drops, all of those gas particles are all of a sudden going to be moving much more slowly and they're going to take up less space. And so the volume temperature relationship is a direct relationship. So as the temperature decreases, the volume will decrease, and as the temperature increases, the volume will also increase, and this would be at constant pressure if we want to maintain constant pressure. And again, here's what it looks like in terms of the math of it. This is a direct relationship. And then the third relationship is called Gay-Lussac's law. This is a pressure and temperature relationship. And so this is just saying that if we want to maintain constant volume, if we increase the temperature at constant volume with the same amount of gas and the same amount of space, we're forcing the particles to move faster and faster, which is going to mean that the pressure is going to increase. And so a common example of this is on the first few days of really cold weather in the winter. Oftentimes your car will tell you that you need to put air in your tires because all of a sudden all that air that was in your tires, all that gas that was in your tires when it gets really cold is condensing, it's getting closer together, and so the pressure is dropping. Those particles are just moving more slowly. So this pressure-temperature relationship is also a direct relationship. As one increases, the other increases, or as one decreases, the other decreases. And again, here is the mathematical relationship between pressure and temperature. So the final gas law that we're going to look at is called the ideal gas law. And the ideal gas law is used, so all of those previous three were all looking at sort of an initial set of conditions and a final set of conditions, holding one variable constant and looking at the relationship between two variables. And the ideal gas law says in a single set of conditions, if we know how much gas we have, if we know moles, then we can predict all of these other factors. And so you're going to spend some time later watching a Khan Academy video that's all about the ideal gas law and focuses on the ideal gas law and this idea of moles and the gas constant. But I just wanted to give you a quick intro to the other gas laws and just thinking about relationships between particles and gases. And I'll see you guys soon.